Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, now in this video you will be learning about the solution of paragraph 35 and 36, question number 35-36 of physics paper 2 generally advanced 2014. So let us see the question of this paragraph question number 35 and 36. Okay. Hello students, now we will see another paragraph which is question number 35 and 36. The figure shows a circular loop of radius A is a circular loop of radius A with two long parallel wires. Here the two long parallel wires, number 1 and number 2, number 1 and number 2, number 1 and 2. Base number is this one, wire 1 and wire 2. They are all in one plane. The distance of each wire from the center of the loop is d. From the center of this loop, this point, the wire is at a distance d. Here also d, equidistant. The loop and the wires are carrying the same current. Whatever is current flowing here, the same current is flowing here. That current is I. The current in the loop is in counterclockwise direction. So you can see here the current here is in counterclockwise direction and the value of current is I. If seen from above. So if you see from above, you will see that current is flowing in anticlockwise sense, and in the same plane there are two parallel wires kept at a distance of d from the center of the circular loop. Now you have to see the question and then solve. What is the question? Let us see the question. The question says that when d is approximately equal to a, d is approximately equal to a means these are the two parallel wires, and this is our d. These are the two wires. What is PQ and RS, infinitely long, and the center is somewhere here, but the radius of this wire is now A, which is nearly equals to D, but wires are not touching the loop. That means the wire will be around, the loop is approximately equal to this, not touching, but then this A is approximately equal to D. In this case, current is flowing in anti-clockwise sense. This is the situation. It's found that the net magnetic field on the axis of loop is 0. It's found that the net magnetic field on the axis of the loop. So this is a loop and the axis will be like this. So in this plane, the axis will be vertical, is 0 on the axis at a height h above the loop. So from this point you go up to a height h, and then that height h, B is net magnetic field, B is supposed to be 0. If it is 0, in that case, which of the options is correct? Let us read the options. Current in wire 1 and 2 are in direction PQ, in this direction, and in this direction, means current is in the same direction, and H is approximately equal to A. Current in 1 and 2 are in PQ and SR, and h is approximately equal to a, and so on. So basically you have to find the relation between h, the height, the loop is in this plane, the wire is here, another wire is here, this is the axis, and at a certain height h here, the wires are like that, the point is here, so wire is here, point is here. Now this h and this a, radius of this loop a, what relation they have for the magnetic field to be 0 at this point. So now first of all, the loop is in this plane, and suppose this is a plane I'm considering, and two wires are kept like this, and the coil is here. Now coil is current is anti-clockwise, so the magnetic field will be up in this direction. This has to be always like so, and only the options we have that we can change to get the magnetic field 0 is that because of the magnetic field contribution by 1 and 2, these two wires, the net should be downward and it must be equal to the magnetic field produced by the loop. That means these two wires must have magnetic field in the opposite sense, in the downward sense, and that must balance the upward magnetic field due to the coil. Now if I have current, two wires are like this, in between there is a coil. If the current is in this sense, in the first wire, if the current is like that, that is from P to Q, then if I hold the conductor like this, the magnetic field will be inside the loop at the point whatever it is, h is downward. So if this side is downward, but the point is at a height h above, but still it will be in this side, but not vertically downward now, because the point is not at the center of the loop but at a certain height h. Then in that case, so if the point is here, the coil is on the plane. If I talk about the point at center, then magnetic field will be cross because of this wire. This side is up and this side is down, because this side will come and this will go into paper down, vertical downward. But if I take a point above this plane at a height h here, that time the magnetic field due to this is not vertically downward. That is the thing, that's the point you have to understand. But it will be in this side but not vertically downward, with certain angle with the vertical. So if that is the case, then it must have two components, one along this side, one along this side. One have a vertical component and the horizontal component. If I want to cancel the horizontal component, then in this wire the current must be not in this sense, because if it is in this sense, then this side it will be up, so it will be something like that, and in that direction it will not balance or will not add to the downward value, because they will be equal. They are equal distance, they will cancel out. The vertical distance will cancel out. So therefore the current in this side, in this part, should be in this sense. So that means it is from S to R. If it is from S to R, then in that side it will be downward. One, due to this wire it is downward like this, due to this wire it is like that. So resultant of these two will be downward. That component, the addition of the two vertical components will balance the magnetic field due to coil which carries a current. So now we have due to this wire, the magnetic field at a height h point, this point is like this, and due to this wire at the height h it is like that. We have to take the resultant of that in that direction, and that resultant, because the horizontal component will cancel out, the vertical component will balance this, and then you have to solve. So this situation you have to understand like this. Now I'll draw this in the separate diagram here. The situation is, this is the wire, this is the wire, the center is here of the coil, and this distance is A. This distance is A. The height is h, but this is not in this plane. You must remember, this is in this height is like that. So to remember that. So don't think that this line and this line are parallel. Rather, they are vertical like this. So this line is vertical, not like this. So you don't think of this now. And this line is suppose R. So what is the situation I am telling you? This is the center of the coil, this one, and this height is h, this one. This distance to this distance is A, and this distance, this height is h. So this is A, this is h, and this distance is R. You can see, suppose this is the coil center. Now you can see here that this point to this point, it is the coil is kept like that without touching the wire. So this distance is A, this distance is h, and this distance from here to here, this is R. If this is R, then at this point the magnetic field, if the current is in this sense, then the magnetic field I will apply Biot-Savart law. This is I dl cross R. R vector is from here to here. Then I dl in this plane, the plane is like that. This is the plane now. I dl cross R. So it is in this plane, I dl cross R. It is like that. You can see this plane. So in this plane, that I dl cross R has to be perpendicular. I dl cross R has to be perpendicular. So it is in this sense. If I find R cross I dl, it is like that. In this sense, this is the plane, and it is like that. So it will be like this side, because ideal cross R, it will be in this side, right? So basically the magnetic field is in this sense, in this side. This is the direction of B. If this is the direction of B, then what angle? So this direction, what angle it makes with this? Because I want to resolve this vector along this direction and along this direction. This is B or B1, whatever you say, and what is this angle? If in this triangle I consider this angle as theta, so in this triangle I will consider this angle as theta. The magnetic field is something like that. It is perpendicular to this plane. If I want to draw the plane, suppose this is the plane I am drawing. To this plane it is perpendicular. So to this plane, like this, and this one is this length. This one is this length. This is the plane, because this is the height, this is the radius. So this is the plane, and this one represents ideal, and this one is your R. Ideal cross R is like that. You can see it is like this. So it is perpendicular to the plane. It is in this direction. It is in this direction, because it has to be perpendicular to both. It has to be like this. So this is what I've done with this one. This is the magnetic field. Then what angle it makes with this line? This line, it makes an angle of 90 degree, because this has to be perpendicular. So this makes an angle of 90 degree with this line. This and this total angle is obviously 90 degree. Then what is the angle it makes with this one? What is the angle it makes with this one? Interestingly, we have to just imagine that this can be like that. This one is angle theta, so this angle will be 90 minus theta. So this total angle is 90, so this angle will be 90 minus theta. So this is the direction along which B will act due to the wire 1. Current is this from P to Q. In this sense, current is I, and this is wire 1. So magnetic field is B1. Now I resolve this vector into this, in this direction and in this direction. So there is a vertical component which moves along this line H. And what is that H line? That H line, here the coil also is the axis, along the axis of the coil. This is basically the axis of coil. Now, similarly, if I think of this wire and current is downward, because I have to have a vector along this direction, to have a vector B1 just like this in this plane, if we think of, then if I have another situation here, this is the situation, and this is the line I have to join, then this plane, so it will be like that, like this plane, then it will be in this direction. So I will whatever this will contribute this side, the same this will contribute this side, because current is same. So I will consider the current, as the name suggests, name is SR. So wire 1, current is P to Q. Wire 2, current is S to R. Wire 1, P to Q, S to R. So these two options I have to see, S to R, this one and this one, and then see which of the option is correct. S to R is here. So these two options I will see which one is correct. Now this is B1, and due to this coil, the magnetic field due to coil at height h along the axis must balance with the component of this vector 2 times this, because this one will also contribute like that. So 2 times because the horizontal component will cancel out, and only the vertical component will add up. These two, B1, B2. This is B1. If this is 90 minus theta, this is along this line, it is B1 sine of theta. B1 sine theta, and similarly B2 sine theta. But B1 and B2 in terms of magnitude they are same. So it is 2B, say 2b sine theta. So let us not write b1 and b2, only write b, so 2b sine theta. So that must balance with 2b sine theta is the magnetic field due to, this is the component of magnetic field due to both wires. So if I see that because of a coil at the axis we have the formula, so B coil equals to 2B sine theta. For coil along the axis at H, the magnetic field will be mu naught upon 4 pi 2 I pi a square, a is the radius of the coil, divided by a square plus h square to the power 3 half. This part is this one and this part is 2b. For a coil at a distance x, current carrying is I, the magnetic field formula is mu naught upon 4 pi 2I by x. For this coil, A is not the distance. The distance is, we are concerned with this point, this is the distance. So this is the wire and this is the point. So that distance R we have taken. In the diagram you can see here, this distance is R. So mu naught upon 4 pi 2I ISM divided by R, and this is for B, this is 2 because there are two wires. Theta, sine theta you have to find out from this triangle, sine theta is this side upon this side, that is A over R. Now if I solve this, this implies that mu naught upon 4 pi will cancel out, 1 A will cancel out, 2 will cancel out, then we have I cancel out, you have pi over here and A there, divided by A square h square power 3 divided by 2, that is equal to 2 is there, divided by R square. Now what is this A square plus h square? You can see from this triangle that A square plus h square root is R. This is the hypotenuse, this is the perpendicular, this is the base. So R is A square h square to the power half. So I can write R in place of this, substitute that, then this will have pi A by R cube, because half power of this is R, so R raised to 3. This is 2 upon R square. Then I will cancel this and 1 R is left. This implies that R equals to pi A by 2. So from here I will proceed to have a relationship between H and A. So R has nothing to do. So I will replace R by, again I will replace R by, again with the same value, that R is A square h square root So this r equals to pi a over 2. If I take the square on both sides, then this becomes a square h square by 4. From here, h square is pi square by 4 minus 1 into a square. This goes to that side, taking a square common, this. So h becomes, this is approximately 10. 10 minus 4 is 6 by 2, 6 by 4. So approximately it is 6 by 4 a square root, which is 2 comes out, a comes out, root of 6. Approximately it is 2.4 something. 2.4. If I take 2.4 root of 6, I'm approximately taking 2.4. Then this is a into 2.4 divided by 2. This becomes h is approximately equal to 1.2 a. If I see the option, h is approximately equal to 1.2 a. Here also h is approximately equal to 1.2 a. So therefore option number 3 is correct. Okay, this is how you solve this question. Thank you. So we'll see that in the same paragraph we have question number 36, which says consider D much greater than A. If I have the diagram over here, the D is much greater than A, means A is very small. If A becomes small, then this will be very large. So smaller coil it has taken, and the loop is rotated about its diameter parallel to the wire. Diameter parallel to the wire. So the wires are like this, and the diameter parallel to the wire is like this. This diameter is parallel to the wire. So this is a coil, and this is the diameter we have to consider. And what you have done, it is rotated about its diameter. So about this diameter, how it will rotate? The coil will rotate like that. This way it will rotate, or this way it will rotate. So it will rotate in this vertical plane by 30 degree from the position shown in the figure. So the first position is that in this plane the coil is placed in this plane horizontal. Now it will rotate it. If it rotates, it will become inclined to the horizontal. It will make certain angle with the horizontal. If the currents in the series are in opposite directions in the size, this should be wires, this would be wires. If the currents in the wires are in opposite directions, the torque on the loop at this new position will be, assume that net field due to wires is constant over the loop. Basically, if you take a large loop, then at each point inside the loop the B will change, because B depends on the distance of the wires, because from the wire that B varies inversely proportional to the distance. Because the loop is considered very small, because D is given much greater than A, means that A is very small. The stress on the D much greater than A is that the area is so small that at each and every point the wire is very far off. So that particular area, at all points, the magnetic field is constant. If the magnetic field is constant, then so that magnetic field, net magnetic field of the wire is constant over the loop. This is constant. Then what is that torque? You have to find. This is the torque equation. You have to find the torque. So then what is that torque? Situation is that now initial position of the coil was this, current in anticlockwise, and this is the direction of the dipole moment, magnetic dipole moment of the coil. As the coil turns, this one is the direction of magnetic dipole moment of this loop. As the coil is tilted, you can see that the M also is turned. If the coil is turned by 30 degree, suppose this is the plane with respect to this plane, this is turning by 30 degree, this one is 30 degree, then this also turns by 30 degree. Then in new situation, this will turn by 30 degree. This is a new situation, new position. This is a new position, and in this new position the coil is also turned like so. By what angle? With respect to this is 30 degree, we have turned it. Now the torque on the coil is given by the expression torque on coil is M cross B. And if you want to find the magnitude of the torque, direction is obvious, that pointing in that sense, the coil is rotating like this. So rotation is this, then it is in that direction. Now magnitude will be MB sine theta. M is this one, that will find. B is the, in the same situation of the wire, that current is in opposite sense, because opposite sense, one this side, another down. So then it is downward, and that side also downward. So due to this one, the magnetic field is downward. Due to this one, the magnetic field is downward. Initially it was downward, and that was, this B was twice the value. This B was due to the wires, and this M is due to the coil. And theta is the angle between this M vector and this vector. So if this is 30, then this vector is downward. This is your B vector. Then if this initial position, it was 180 degree, now it turns by that, so this goes to this place. Now this is the angle, this is the angle. Initially it was 180, now this is the angle, which is 150, because this is 30. Through whatever angle the wire, the coil rotates, the same angle the m will rotate. Then I'll substitute this value of theta as 150. Then this is mb sine 150. Now what is m? M is the current flowing in the coil, that is I, and the area of the coil, that is pi a square. B is the magnetic field due to each, and it is the same, so to make double, twice the value of B due to each wire, and each wire it is mu 0 upon 4 pi 2I by, this distance is D, 2I by D. And sine of 150 is equal to sine of, this is 180 minus 30. Sine pi minus theta is sine theta, so it is sine of 30. So it's half. So then we'll have torque equals to I pi a square. I'm just rewriting that, 2 mu naught divided by 4 pi 2I by D sine of 30. Okay, what I'm doing is just this value I'm just rewriting here. Now this pi 4 will cancel. This sine 30 is half, so write I and I is I square, a square mu naught, and this is half is 2D. So this comes out to be mu naught I square a square by 2D. If I see the option here, mu naught I square a square by 2D, mu naught I square a square by 2D, so this option is correct. So option number 2 is correct. Okay, thank you.